Today we're going to look at an introduction to this programming language called Clojure. So object-oriented programs are often collections of many interconnected objects. So here each object has its own state, and the state of an object is a combination of all the values in the data members. So here looks like we have a series of these point objects. Maybe each one has an x and a y coordinate value. And we have a line object which has references to these different points. It's not unusual to have hundreds or thousands of objects in memory at any one point in time. And making one function call can cause a chain reaction of changes to many objects' state. So here, if we, using the line reference, if we said line.move 1010, what that means is we want every one of those points to maybe move 10 in the x direction and 10 in the y direction. Okay, we'll see that a lot of these objects are going to change. Their internal state is going to change. Each xy has to be altered. Okay, so the effect of what looked like a small change, just one method call, line.move, might be quite large and might be difficult to comprehend. When you make a function call like that, line.move, you might not even realize all of the internal objects that are going to change. Now when you add concurrent updates from multiple processors into the mix, this gets even more complex. So let's say our points are up here in RAM, but now we have multiple processors. And let's pretend that each one of these processors at exactly the same time executed these calls. So this one says line.move 1010. That means that we want all of those points to move 10 and 10. This CPU, with the same line object, right, because everything in RAM here is shared by the CPUs, says, well, move back 5 and 5. And then the interesting one is, well, what do you think is going to happen when this CPU says line.draw? You know, are most of the objects going to be moved 10, 10? Are some of them going to be moved only 5? Are some going to be moved negative 5? There's a big question mark about what's going to happen when we draw, when we have these multiple processors. Okay, so the big question is, what is the state of the line if multiple CPUs are executing that move method at exactly the same time? Now, functional programming languages ease the burden of state complexity by not allowing state to change, or if it must change, doing it in a very safe and controlled way. In other words, functional programming de-emphasizes the complex interconnectedness of objects by limiting the effect one state change can have on another. Now, some may argue, however, that having all of those interconnected classes is actually a pretty good way to organize certain types of complex systems. This is, after all, the hallmark of object-oriented programming. So you're going to have to make that judgment for yourself. I would like you, though, to keep an open mind. Clojure is a functional programming language that runs on the JVM. This is the same environment that Java programs run on. All of the Java libraries that are available in a Java program are also available in Clojure. So I know most of you know some Java. That we know there's built-in GUI code, threading code, networking code, etc. Like many functional programming languages, Clojure is called a Lisp, or a list processor. Okay. With Lisps, lists are important. Almost everything, including the executing code, will be in some kind of a list. With imperative languages, the programmer writes statements to alter the state of objects. That's pretty much the definition of an imperative object-oriented programming language. Changing the state of an object, that's kind of a front and center operation in C++, in Ruby, in Java. In Clojure, data is mostly immutable, which means that it can't be changed after an initial value is given to the data. Now, there are safe ways of simulating changing the data that we're going to talk about shortly, but there are none of the state-related drawbacks mentioned above. If data is unchangeable after its creation, then there's no risk that two competing threads will overwrite each other's work. which is what we typically call a race condition. Now, functions are also very important in Lisps. Functions are supposed to be side effect free. All of the code inside a function should contribute solely to its return value. Anything that doesn't contribute to the function's return value is called a side effect. Now, calling a function should have no effect on the outside world. Calling line.move on a line object has the side effect of changing many different point objects. These are side effects that have nothing to do with generating a return value. And in fact, the move method might not even return a value. Some languages have different names for blocks of code. So in some languages, a function is a name block of code that always returns a value, whereas a procedure is a name block of code that doesn't return anything. Okay, in Clojure we always create functions. Functions are always supposed to return a value. Now, a pure function has no side effects and does not change any shared state. One puts a value in and gets a value out. With the same inputs, the same value will come out no matter what the state of the variables are. Okay, this is very similar to the idea of a mathematical function. Okay, so there are no conditions such that if you plug in a 2 to this function x squared, that you are not going to get 4 back. Using pure functions makes programs easier to comprehend and test because you can see exactly what effect a function has, and you don't have to worry about any hidden side effects. That's always a big issue with object-oriented programs, is you have to wonder, does calling this method affect other objects that I'm not aware of? Now, in an introductory programming course, if you've had that with me, you've probably heard me say that you should never use global variables in a program. Okay, but you might have noticed they're a lot easier to use since you don't have to learn all that ugly parameter syntax. However, global variables make it too easy to introduce these side effects. Okay, and side effects tend to cripple a program. So in those introductory courses, I say don't use global variables because really I'm trying to help you. Because chances are you'll do something incorrectly with a global variable where if you pass it as a parameter, you're less likely to hurt yourself. Now, since functions are isolated, this means that they can be passed to other functions or returned from functions. And functions that take or return other functions are called higher order functions. We're going to spend a lot of time in a future video talking about those. Clojure provides a REPL, which is a console for experimenting with Clojure. And REPL is an acronym for Read, Evaluate, Print, and Loop. This is similar to IRB in Ruby. So in the REPL there's a reader. The reader parses all the tokens that the programmer writes. The reader separates all of the lists, the numbers, the strings, the functions, etc. We also have this thing called an evaluator. And the evaluator evaluates the parsed tokens and returns a value. So what it means to evaluate the parsed tokens means basically to execute statements to produce values. Okay, and when we return a value, that might be used later in some outer evaluation. We have a printer which prints out the output, and then the REPL repeats this process. So that's what the loop is for. Okay, I'm going to use a REPL here. So I happen to be using this tool called IntelliJ, and I'll be using that in all my videos to execute Clojure code. But I'm going to do just a couple things here. Don't worry about understanding exactly what's happening. Okay. So what I just did there was I added 1 and 1 together at the REPL, and the REPL told me the sum of 1 plus 1 is 2. Okay. There's another built-in function called str, which concatenates strings together. Okay, and when I hit enter here at the REPL, we'll see that in Clojure we concatenated all these strings together into one big string. In all Lisps, lists are very important. Clojure is a list, so lists are a fundamental data structure to the language. A Clojure list is roughly equivalent to a linked list with nodes and pointers. Okay, so you might remember this from the data structures class. The syntax for lists are represented with a series of items inside a set of parentheses. Okay, so here's an example of a list of integers. Okay, the parentheses indicate that this is a list. So if we were to look at a picture of that list, it would roughly look something like that. Now, turns out that with these lists, commas are optional. Commas are actually considered to be white space. So here's a list of some integers with commas, and here's a list of some strings that don't happen to have commas. And either way, that's totally fine. Clojure also has a data type called a vector. And a vector is roughly equivalent to a C++ vector or a Java array list. So it's an array-based collection. It's not a linked list-based one. And the syntax for a vector is similar to a list, but you use square brackets instead of parentheses. Okay, so here's a vector of integers, and here's a vector of strings. Okay, the implications between an array-based collection versus a linked list-based collection are the speed with which one can find, insert, and remove a value in the middle. So refer back to your data structure notes for more information on that. That whole course was basically examining the different data structures. When we're writing code in Clojure, though, for the most part, we don't care whether we're using a list or a vector. This is a pretty low-level detail that, unless we have some serious performance constraints, we can mostly ignore. Now, one nice thing about the distinction is that it's easy to spot the difference in code. For most of the functions we write, our parameter lists are going to be vectors. So don't worry too much about the syntax here, but this is a function called hello, and it has a parameter list. We have one parameter inside this function called name. Okay. And I know this because the square brackets, we use the vector to indicate our parameter list. It sticks out from all the other parentheses that we have. So traditional lists have lots of parentheses. So having these square brackets really helps set the collections apart. Now, lists and vectors are in a family of sequences, or seeks. Sequences are, very abstractly, things that can be iterated over. They share many of the same characteristics. The most important feature that all seeks share is that there are common functions that allow the programmer to manipulate the contents of the seeks. Soon we're going to see the functions map, filter, every, and many more. Okay. Most of them are going to work with a sequence, whether it's a list or a vector. It usually doesn't matter. Now we have other types as well. We have something called a hash map, or just a plain map. That's a collection of key and value pairs. And maps are identified with curly braces. So again, if you recall the data structures course, we created this thing called a hash table. Okay, a map is basically a hash table. Okay, so here are a couple maps. We have key and value, key and value, and so on. This first one uses commas to separate the key-value pairs. The second one doesn't use any commas. And this may seem a little bit hard to read, but after a while it becomes easier to read. Okay. So notice the map is made up of key and value pairs in that order. Okay. There's another collection called a set. And a set is a collection without repeated values. And we identify a set with curly braces and this pound sign. Okay, so again, this is kind of a generic container, but no repeats are allowed. Okay, so we have a list, a vector, a map, and a set. Those are our main data structures. Now, we don't really create traditional object-oriented classes that contain data and are smart, meaning they include methods that work on that data. Instead, we stick any required data into one of these containers and then pass the containers around to independent functions. And what this means is there are very few hidden side effects. So what happens when you run a Clojure program? When you run a .clj file, a reader reads in the forms and parses the text. The reader generates Clojure data structures that are then sent to a compiler. The compiler creates bytecode that is then executed or interpreted on the JVM. A list can hold traditional data to be used in our program, but it's also how we call our functions. The default behavior when an evaluator gets a list is to treat the first item in the list as a function, and to call it with the rest of the list as parameters. And we call this style prefix style. And this is going to feel a little funny at first, right? So the Java way of doing things is we put the name of the function first and the parameter list second. Okay. A more Lispy way of doing this is to have a list. So I know this is a list because I see the parentheses, with a function being the first thing in the list, and everything after that first element are the parameters. Okay, and what an evaluator does is whenever it sees a list, it tries to treat that first item as a function, tries to call it, and it passes the remaining items into that function. Now the arithmetic and relational operators or functions are going to feel funny because those we're used to using this infix style, but it does get easier with time. So let me go back to the REPL and start to execute some functions here. So we'll start with plus 1 and 2. This is how we add the numbers 1 and 2 together. So plus is the name of a function. The parameters are 2 or more numbers that we're going to add together. So 1 plus 2 is equal to 3. We can put actually more than 2 numbers here. So the plus function will iterate through all these values and keep a running sum. 1 plus 2 plus 3 is 6. If we wanted to subtract 5 from the value 10, 10 minus 5 is 5. If we wanted to multiply 3 and 4, 3 times 4 is 12. If we wanted to divide 22 by 7, these are the floating point numbers, 22 and 7, we get about 3.14. If you want to work with integers and do division, there's a special function called quote, which will give you the quotient, and rem will give you the remainder. Okay, we can use the relational operators. These are the ones that I said are going to feel a little funny at first. This says, is 5 greater than or equal to 4? And the REPL is going to tell us, yes, that's true. 5 is greater than 4. Here we're going to say, is 10 exactly equal to 100? This should be false. Okay. There's a function called even with a question mark that says, is the number that gets passed in, is that even or not? And that is true. And you could probably guess there's one called odd, which will tell you if a number is odd or not. There's a function called number, question mark, that tells you, are the parameters here, are they numbers? So 2 is a number. If we called number and we pass in the plus is a function, so it should return false. Now there's also a function called function question mark. Right, so this says, is the plus a function? That turns out to be true. Okay, notice the last two cases here. We actually passed in a function to another function, or we had a function as a parameter to another function. The passed in function was not called. So here plus, we weren't really adding anything together. So plus didn't end up getting called. It was just treated like a piece of data. And in this sense, we can see that executable code, like a function, is just like any other data. In fact, the code, the Clojure code that we write is data, and we can actually manipulate it. Okay, let's look a little more closely at that first statement I said, 1 plus 2. Okay, so what happens? Well, a reader parses 3 elements into a list. Okay, and then the list is sent to an evaluator. The evaluator creates 3 sub-evaluators to ask each token to be evaluated into something. Now the first sub-evaluator determines that the plus token is the name of a function for adding, and it retrieves that function object. The other 2 sub-evaluators determine that 1 and 2 are numbers and just return their values. Now the original evaluator receives a function and 2 numbers, and remember, whenever the evaluator sees a list, it treats it as an excuse to call the first item in that list as a function. By default, this is what evaluators do. It applies the add function to the 2 numbers, and it returns the value 3. Let's look at a slightly more complex evaluation here. So plus times 3, 4, 2. Okay, here the evaluator creates 3 sub-evaluators, and the middle sub-evaluator creates 3 sub-sub-evaluators, and eventually receives the value 12. Then the topmost evaluator receives the plus function, 12, and the number 2, which it then evaluates to the number 14. Now parentheses force the order that things are evaluated, like in most other programming languages. Sometimes we want a list just to be a list of data. Right? We don't want to call a function. This is when we quote a list. Okay, so let me take this code here, put it in the REPL, and see what happens. Okay. So we get this error message, cannot cast a, the long cannot be cast to a function, is basically what this is saying. So it's looking at this first thing in the list and it's saying, well, 1 isn't the name of a function. It can't possibly call that as a function. Okay. Let's take this code, though. Put it in the REPL. Okay. And now we see we don't get an error message. In fact, the REPL returns what looks like a list with the numbers 1, 2, and 3. So the quoted list says not to treat the list as a function call with parameter data, which is the default behavior, and just treat it like a plain old collection of data. Okay, so occasionally you're going to see me write lists with a single quote in front of it, and just keep in mind, if you don't do that, the evaluator is going to try and execute that as a function call. But with that quote, it'll just be considered a simple list of data. When an evaluator receives a vector with square brackets, it evaluates each item on the vector and then wraps the return values up into a new vector. Okay, so because of this, there are times when we're going to quote a vector as well, when we don't want the items to be evaluated. So for example, if we wanted a vector with names of functions, but not the actual function objects, we would quote a vector. With the quote, the names of the functions would be evaluated, without the quote, the names of the functions would be evaluated to actual function objects. Okay. So what this says is, if the evaluator were to evaluate this, it would go and try and find 2 function objects, foo and bar, and put them in a new vector. Whereas this quoted vector says, Well, don't evaluate these. Don't go and try and find functions called foo and bar. We just want to store these names, okay, and we don't want them to be evaluated. In Clojure, you can name things using the def function. This assigns a name to a piece of data or a function. So def is a function that allows you to bind a name to a thing. And it pretty much looks like this. Okay. So now name will be replaced with thing whenever it's evaluated by an evaluator. So let's go back to the REPL. And we'll see I've defined this thing called person's name to be equal to Mark. And I've defined this person's age to be 41. Okay. Now if I were to refer to person's name, you see the REPL returned the value Mark. And if I say person's age, that's the value 41. Okay, to show you maybe a few more examples, let's manipulate some maps. So maps, when they're the first element on a list, they're treated as functions. A map actually becomes a function, where you can pass in a key, and the value associated with that key will be returned. So let me get some code here. Okay, so what we have here is I'm defining this map called schools. And again, I know this is a map because of the curly braces. And we have these key and value pairs. So anything that starts with a colon is called a keyword. And it's very similar to, we've seen something similar in other languages like Ruby. It's basically used to name things. So this says the key is going to be Carthage and the value is Kenosha, Wisconsin. The key here is MIT. The value is Cambridge, Massachusetts. The key is Stanford. The value is Stanford, California. Okay, now when I say schools, that's the name of the map. If I put that in a list as the first parameter, we're going to treat schools like a function. And we're going to search that map for the key, Carthage. Okay, and actually, let me take that part out. Okay, and now when I execute this, this is the output when I called def. Right, this created the schools map. And then this is the output when I tried to pull out the value Carthage from schools. And it turns out keywords can also be used as functions. So this is kind of the opposite or the inverse here. If you pass in a keyword as the first item in a list, it'll be treated as a function, and we'll search for that key inside this map. And we see that we got Kenosha, Wisconsin a second time. I've said a few times now that Clojure data is immutable. And this means that once you give a piece of data a value, it cannot change. It is immutable. But you might be wondering, well, how can that possibly work? How could we write a program where we can't change the values of a variables? We need to be able to change that data in order to do anything useful, right? Well, let's consider for a second a list. If we would like to add something to a list, we can do that using the const function. And const is short for construct. Okay, I'm going to take this code. Put it in the REPL. Okay, so this says const the value 1 with this list with the values 2, 3, and 4. And what the REPL returns is a new list with the value 1 followed by 2, 3, and 4. Okay, well, let's do that again, but let's store the values. Okay, so now we're gonna const the value 2 with the list 3, 4, and 5, and we're going to store that inside a variable called newList. And then we're going to create another variable called newList, where we're going to const 1 to the value of newList, which again will be replaced with this list that should have 2, 3, 4, and 5. And then I'm going to just evaluate newList. Okay, so this 1, 2, 3, 4, 5 is what happens when we evaluate newList. Okay, so again, newList should hold 2, 3, 4, and 5, and newList, since we const that value 1, const always creates a new list with an additional value added. Okay, so since data is immutable in Clojure, we can't actually alter newList. Other people who are using it expect it to always hold those initial values. Okay, it can never change. You might be thinking, well, okay, if we can't change the list, then if we want to have newList, we're going to have to make a copy of each item when we do the const. In other words, we started with newList, it looked like this, and if we const the value 1 and newList, you might think we have to make a brand new linked list here and copy all these values 2, 3, 4, and 5, and then make sure 1 is at the front. In other words, we have all these redundant copies of values clogging up our RAM. Now this certainly would be one way of accomplishing a const operation, but it's not very memory efficient. After all, we're really only adding one value at a time with consts. That's the way it works. If we did this repeatedly, say 1,000,000 times, we would have many, many redundant copies of different parts of the list occupying our memory. In other words, if I had a list with 5,000 phone numbers on it, and I wanted a new list with those numbers plus just one more, then I would need to copy the 5,000 numbers and then add the one new phone number. This would be a pretty terrible way of dealing with immutable lists. Luckily, the situation is not as bad as you might expect. Each list can actually maintain its own identity and be used to build upon. So let me show you what really happens to newList and newList. So newList does hold those values 2, 3, 4, and 5. But when I created newList by consting the value 1 and the list called newList, all const does is it creates one item and then creates a link, okay, or a pointer to all the other items in this list. So newList isn't really taking up that much memory. It's just got the room for the one piece of data and a room for the pointer to point to the original list that we're consting to. Okay, so when we const, an entirely new copy of the list is not made. Instead, a new element is created that points to the rest of the list. This is both memory efficient and permits data to stay immutable. Now there are methods that we can use with all sequences that take advantage of this. So we have first, rest, and nth. Okay, so let's execute these in the REPL. Okay, so first, when we pass in newList, that should give us the value 1, because that's the first item. Rest, when we pass in newList, that should return the values 2, 3, 4, and 5. That's, in other words, apart from the first one, it's the rest of the list, or basically newList. And then nth allows us to go grab a zero-based index from the list. Okay, so we see this is the output in the call to first. Right? This is the output in the call to rest. Right? That's the 2, 3, 4, 5. And if we go to position 3, let's see, 0, 1, 2, 3, that should give us the value 4. That's the output that we see down here. Okay, so this efficient storage technique works with other data types as well. So maps are very important in Clojure. There's a function called associate that adds an element to a map. Okay. So let's look at this code. So we're creating two maps here. We're creating a map of people's ages, and we call this map ages people. Okay. And then here's the associate function, which is basically going to associate a new key and value pair to an existing map. So we're gonna add Willie the cat's age to this map, and we're going to call this new map ages people and animals. Okay, so if we look at ages people, that has all the humans, and if we look at ages people and animals, we see that this also looks like a map, but now notice we have the cat's age in there, along with all the human ages. Okay, so when we call this associate function, it does create a new map, but it uses the old one to build upon. Okay, so let me give you another example here. I won't actually execute this code, but let's pretend we had two maps. This one's called huge map, and it has a kind of a series of letters and a keyword here, and a corresponding number associated with basically all the combinations of letters. So B is 2, C is 3, Z is 26. Then we'd wrap around AA is 27, AB is 28. And then if we had 6 Z's altogether, that would be a pretty large number. Okay, so that's a pretty huge map. But notice I forgot the A, right? So if I wanted to create a new map that has the value A in there, I could associate the huge map and add this new key and value. Okay, and we'll store that inside this thing called huge map version 2. So you might be worried. You might say, my gosh, now we're going to have two huge maps sitting around in memory. Okay, but that's not actually how it works. This does not make a copy of the huge map just to add one new key value pair. Instead, links or pointers are used to associate that new key value pair to the old ones. Okay, so this there's a good picture that we could look at here. Here's the huge map. That was the original one with all those different values. And then after we do the associate, okay, what that means when we do this with maps is now huge map version 2 has this very small map. It just has a key and a value, but it also has a link to a much bigger one. And now if we were to go and look for a value in huge map version 2, all this really means is look here first. Is the key that we're looking for in here? If not, follow the link here to the next position here and look for a key there. And if it doesn't happen to be there, but there's another link to another map, we just keep following these links until we either find what we're looking for or we get to the end and we haven't found it. In that case, we could handle that case. Okay, so again, we get the benefits of immutability and very efficient storage. So this is a really important picture here. This one and this one. You always want to keep it in your mind that Clojure does things pretty intelligently. It very rarely allows us to store redundant data. Instead, most times we have little pieces of data with links to existing pieces of data. And again, that allows us to have new lists, in this case, be immutable. Right? Anybody who has a reference to new list is expecting it to have only these values. But we can also build on that. So now the people using new lists, they also have access to all these values plus the new one. Okay, there's some other ways of creating the data structures that we talked about so far. So there's a function called list, where if you pass it a group of values, it'll turn those into a list. There's a function called vector, which will create a vector for you, hash map, and hash set. There's some additional map functions. So there's associate we talked about, there's disassociate, and there's one called merge, which you can look up to see how to manipulate a map in more detail. We can also use def record to create a consistent looking map. So the way def record works is you give the name of a type and then a list of data members, and each data member is going to be converted into some keys. Okay, so if we take this code to the REPL here, this says basically create a data type called student, where every student has a social security number, student name, and a GPA. All it's really doing is allowing us to create a map with those as keys. Okay. The way we actually create a student is we use this arrow notation. This basically says we want to create a student record, and we want the social security number to be 123, the student name to be Mark, and the GPA to be 3.2. Okay, so that creates an actual record. And then lastly, we can treat S1, that's the name of the piece of data that we just created, kind of like it's a map. So we can ask for the student name in S1, and we get Mark. Or we could ask for the social security number, and we should get 123. Earlier we saw the const method, which creates a new list from a single value in an old list. Now the new list contains all the values on the old list plus the new single value. Since executable Clojure code is just lists of functions and parameters, sometimes we're going to want to alter the program by manipulating lists. Now, in a compiled language, this manipulation of the code as the program is running is out of the question. We can't do that in compiled languages. But in Clojure we can. And in order to help us do that, we have something called the apply function. And the apply function combines a call to const and a call to the evaluator so that we can create a new list with a function on it and then have the evaluator in turn call that function. So for example, we may have a list of numbers that perhaps come from a user or a file or something, and then we would like to add all those numbers together. Now the most straightforward way to do that is with a function called reduce, which we'll talk about later, but let's pretend that didn't exist. Okay, what we could do is generate a new list and just stick the plus function at the front of it. Right, so you might think we could execute this code. Okay. This is, after all, a list that has the plus function, and then we have a list of values here. But we'll see this doesn't work. We get this error message. Okay, and here's why. Basically, the plus function expects a series of numbers as parameters, but instead we had a full list as the one and only parameter. Okay. Now, what this apply function does is it does a const and an evaluation. Okay, so basically what this is saying is apply says take this first value and const it to this list 1, 2, 3, and then evaluate that whole thing to generate a value. We should get the value 6 now. Okay, so let's look at this picture. The effect of calling apply with these two things says take the first element and then take each element inside this parameter here, the list, and basically generate a new list and then evaluate it. Okay, so there actually is a function called eval, which we can call if we ever want to invoke the evaluator. Okay, so here what I'm doing, here I'm kind of doing what apply does, but I'm doing it in 2 steps. Const will generate a new list with the plus, and the values 1, 2, and 3. We're storing that in new code, and then we can call eval with new code, and we should get the same value, 6. Okay. So all apply does is it's a const followed by a call to eval, just like I did in my 2 steps up here. Okay, const always adds the item to the beginning of the list. There's another function called conjoin, and there's another function called into, which are used to combine values from different sequences together. Let me show you how they work. So conjoin, you pass in a sequence and then a list of other items. So let's start with conjoin. So here we're conjoining a list with 1, 2, 3 and 2 additional items A and B. And you'll see we get a new list back, or a new sequence with B, A, 1, 2, and 3. Into works similarly. Okay, so we have a vector here, 1, 2, 3. We have another vector with A, B, and C. Okay. Into kind of combines them into one big one. Okay. And this is, again, there's different ways to combine elements together. Like I said, const always, you can only add one item to the beginning of a list. Conjoin, you can add multiple items to a list. And into takes 2 or more lists or sequences and puts them together. Okay, all programs typically require some input, do some processing, and then display some output. Luckily, we can use Java's built-in swing library to do the input and output. Now, I have a video about how to interact with Java that will be up shortly. Let's go to IntelliJ here. And now for the first time, I'm also not going to work from the REPL. So I happen to have a file here called inclass.clj, and I'm going to put all my code in here. So the REPL is nice when you want to work on little bits of code, kind of one piece at a time. But of course, you can also put all the code in a file and run it from there. And that's what I'm doing here. So let me run the program first to show you what it does. Basically just asks for a name and an age, and then it echoes that value back and says what your age will be in 10 years. So I'll put in a name, Mark. Put in an age of 41. It says your name is Mark, you're 41 years old. In 10 years you'll be 51. Okay, so certainly nothing fantastic, but this is using the swing library. Okay, so if you want to use something from Java, you have to import it at the top of the file. And again, import is a function, so it belongs on a list like this. And here we're saying we want to import the JOption pane. Now, in order to call a method on an object, we have this notation here where we create a list that starts with a period or a dot. And the dot means we're calling a function. Then we either put the object or the class, the method name, and then list any parameters that are required for that method. So, what I have here is a call to a JOption pane show input dialog, which you might remember that takes a parent frame, which we'll just put in nil, and then a prompt message. So what is your name? Now show input dialog returns a string, so I'm defining your name to be the string that comes from the show input dialog. Then I do something similar where I ask for the age. Okay, so that returns a string. I need to turn it into an integer, though, if I'm going to do any math with it. So again, I'm basically saying integer.parseInt, except the dot goes here. And it's taking this string and turning it into an int, which I'm going to store in your age. Finally, I'm going to display the output here with the JOption pane show message dialog. So it says your name, and then here I'm using the str, the string function, concatenates a bunch of strings together. So your name is Mark, you are 41 years old. Then I have another dialog that says in 10 years you'll be, and here I do a little math, plus your age 10, we'll add 10 to your age, and then concatenate it to this string. Now I also call printLine. This prints to the console window. So if you wanted to do some debugging or something, you could write to both the JOption pane and the console. Okay, so I don't have my console window up, but I will start to use printLine more frequently. Okay, so that's our basic introduction to Clojure. There'll be several more videos where we'll dive deeper.